Hello, I'm John Andrew Kane Hoveliana, and in this video, we will solve 3 problems on precipitation reactions. This is under Day 1, Physical and Chemical Principles of the Chemical Engineering Board Examination. So for our first question, number 7, determine the volume in milliliters of 5.05 molars silver nitrate needed to react with 25 milliliters of 5.10 molars barium chloride. Letter A, 40.8 ml. Letter B, 50.5 ml. Letter C, 38.2 ml. Letter D, 45.6 ml. So to start this problem, we need to first write the chemical reaction that describes this precipitation reaction. So for our reagents or reactants, we have silver nitrate, which is AgNO3, and barium chloride, BaCl2. And typically, our precipitation reactions are double displacement reactions. So we first write the chemical reaction, silver nitrate, AgNO3, plus barium chloride, BaCl2. The product for this precipitation is given by silver chloride, AgCl, and barium nitrate, BaNO3 quantity 2. And then we balance the chemical equation. So we put 2 here to balance chloride because we have 2 chlorine in the reactant side, and then now we have 2 chlorine atoms in the product side. Then we now have 2 silver atoms, so we put 2 on silver nitrate, and then this time we have 2 groups of nitrate ion, and it matches the other product. So this is our balanced chemical equation. Next, recall that volume in ml times molarity in molars will give us the millimoles of the species. So we need to react with 25 ml of 5.10 molars of barium chloride. So what we can do is multiply 25 ml of this barium chloride. Then the molarity can be expressed, capital M is equivalent to moles per liter, but liter is equivalent to 1000 ml. So in terms of molarity, we can express 5.10 molars barium chloride as 5.10 moles of barium chloride per 1000 ml of solution. So milliliters will cancel. And now we have moles of barium chloride. Next, we need to use the stoichiometric coefficients of the balanced chemical reaction. So our current unit is mole of barium chloride, and we need to cancel that. So we put the unit mole of barium chloride at the denominator. And then what we want is the amount of silver nitrate. So we put on the numerator moles of silver nitrate. So from the chemical reaction, their stoichiometric coefficients are 1, which is for barium chloride here, and then 2, which is for silver nitrate. And then lastly, we can cancel moles of barium chloride, and now we have moles of silver nitrate. To convert that to volume in milliliters, we can divide this mole of silver nitrate by the molarity. So the molarity of silver nitrate is 5.05 molars, and we can express that as 5.05 moles of silver nitrate per 1000 ml of this species. And we can now cancel moles of silver nitrate. So calculating 25 times 5.10 times 2 divided by 5.05, we can also cancel this 1000 here. We can calculate the amount in terms of volume. Calculating, this is around 50.495 ml. So from the choices, this is letter B, 50.5 milliliters. So for our next question, number 8, 1 liter of water initially contains 50 milligrams of calcium 2+ and 50 milligrams of carbonate ion. Determine the final concentration in milligrams per liter of calcium 2+ in the solution when equilibrium is reached. Use pKs of calcium carbonate 8.305. The choices are letter A, 16.7 milligrams per liter, letter B, 14.4 milligrams per liter, letter C, 15.6 milligrams per liter, letter D, 17.1 milligrams per liter. So to start this problem, we are given in terms of milligrams of the species, and we first convert that into moles using their molar masses. So to start, from the Paris Chemical Engineering Handbook, the molar masses in grams per mole of our desired species are calcium 2 plus is 40.08 grams per mole. For carbonate ion, we have 1 carbon atom, 12.01, plus 3 oxygen atoms, 3 times 16. So 48 plus 12.01, this is 60.01 grams per mole. So from the given, we can first calculate the initial concentrations of both species. So, initial concentrations for calcium 2 plus, let's denote that as Ca2 plus subscript 0, we have 50 milligrams of calcium 2 plus. Convert that first into grams. So grams of calcium 2 plus is equivalent to 1,000 milligrams of calcium 2 plus. And then convert grams into moles. Moles of Ca2 plus is equivalent to 40.08 grams of calcium 2 plus. Then, divided by the total volume, we are given 1 liter of water. So, divide by 1 liter. So, cancel milligrams of Ca2 plus, cancel grams of Ca2 plus, and we'll have moles of Ca2 plus per liter. So, the first concentration is given by 1.2475 times 10 to the minus 3 molars of Ca2 plus. So in our calculator, we will use this later, so let us store this to variable A. Likewise, we can also calculate the initial concentration of the carbonate ion. So we have CO3, 2 minus initial, and then the initial concentration is also 50 milligrams of carbonate ion, and convert that first into grams. So grams of carbonate is equivalent to 1,000 milligrams. And using its molar mass, we can calculate the moles of carbonate, which is 60.01 grams per mole. Then, we can divide this by the total initial volume, 1 liter. So we can cancel milligrams of carbonate, grams of carbonate, and we'll have moles of carbonate per liter. So the initial concentration of the carbonate ion is around 8.33 times 10 to the minus 4 molars of carbonate. So since we will use this value, let us store these two variables in our calculator. In this system, the precipitation of calcium carbonate is an equilibrium reaction, which can be expressed as calcium carbonate, CaCO3, reversible with Ca2 plus, and carbonate ion. We can also express its solubility product, KSP or Ks, as the product of their concentrations at equilibrium. So Ca2 plus and CO3, 2 minus. We are given the value pKs, which is 8.305, and to calculate Ks, this is equal to 10 raised to negative pKs, which is equal to 10 raised to negative 8.305. We have calculated the initial concentrations of Ca2 plus and CO3, 2 minus. But in this expression, what we need are the equilibrium concentrations, which is obtained by subtracting the amount of calcium and carbonate that precipitates in this reaction. So we can let X as the amount precipitated per species. So we can calculate Ks, which is equal to 10 raised to negative pKs, which is equal to, for this problem, 10 raised to minus 8.305. This is equal to the concentration of calcium 2 plus at equilibrium is given by its initial concentration, 1.2475 molars, minus X, which will precipitate. And then, the equilibrium concentration of the carbonate ion is 8.33 times 10 to the minus 4 molars, and also minus X. This is the amount of carbonate that precipitates. Based on this precipitation reaction, the amount that precipitates in terms of CA2 plus is equal to that in CO3 2 minus. So they are in 1-to-1 ratio. So from this equation, we can now calculate X, which is the amount of calcium carbonate in terms of moles that will precipitate. So in this unit, we can solve for X, and take note that this form is a quadratic equation. We can solve for two roots using our calculator. The first root is x1 equals 8.21 times 10 to the minus 4 molars, while the second root, x2, is equal to 1.25 times 10 to the minus 3 molars. So we need to take only one root, which is possible. We can see that the value of x2 is greater than the initial concentrations of Ca2 plus and CO3 2 minus. So we cannot use this root for this expression. So x2 here is an extraneous root. So the correct root in terms of x is given by x1. So finally, we can calculate the final or equilibrium concentration of Ca2 plus. So the concentration of Ca2 plus given by its initial concentration, 1.2475 molars, minus the amount that precipitated, 8.21, 5626 times 10 to the minus 4 molars, and then express this in milligrams per liter. So, molars here is equivalent to moles of Ca2 plus per liter, and then convert this to grams, 40.08 grams Ca2 plus per mole of Ca2 plus, and lastly convert into milligrams. So we have 1,000 milligrams per gram. So we can cancel molars, cancel moles of Ca2 plus, and cancel grams of Ca2 plus. So our final value is around 17.07 milligrams of Ca2 plus per liter. So from the choices, the correct answer is letter D, 17.1 milligrams per liter. So for our last problem, number 9, analyze and determine the molar solubilities of calcium sulfate, lithium carbonate, silver phosphate, and calcium carbonate given the following KSP values respectively: 2.4 times 10 to the minus 5, 2.5 times 10 to the minus 2, 8.89 times 10 to the minus 17, and 4.95 times 10 to the minus 9. In this problem, we are given the KSP values and we need to calculate for the solubilities of all species. To start solving this problem, we first need to express the precipitation reactions of the species. So first, we can write calcium sulfate, CaSO4. This is in equilibrium with Ca2 plus SO4 2 minus. Next, for lithium carbonate, we have Li2CO3, and this is an equilibrium with 2 Li plus carbonate ion. Next, for silver phosphate, This is Ag3PO4 reversible with 3 Ag plus phosphate ion. And lastly, calcium carbonate, CaCO3. This is reversible with Ca2 plus carbonate ion. Next, we can express their solubility products in terms of their equilibrium concentrations. So for KSE, for calcium sulfate, this is expressed as Ca2 plus times SO4 2 minus. For lithium carbonate, we can express this as lithium plus squared times concentration of carbonate ion. For silver phosphate, we can express this as Ag plus cube times phosphate ion concentration. And lastly, for calcium carbonate, we can express KSP as Ca2 plus concentration times concentration of carbonate ion. So to express solubilities, we can use the variable S. If they are in 1-to-1 ratio, we can use S for concentration of SO4 2 minus and also S for Ca2 plus. If you have 2 Li plus, then we can substitute 2S, and then for 3 Ag plus, we can substitute 3S. So first, let us solve for the molar solubility of calcium sulfate. So KSP of calcium sulfate, respectively, is given here 2.4 times 10 to the minus 5. This is equal to the concentration of Ca2 plus and concentration of sulfate ion. So we can express that as S. So S times S, which is S squared. So 2.4 times 10 to the minus 5 is equal to S squared. So calculating for S, we can have S 4.8989 times 10 to the minus 3 molars. So this is the solubility of calcium sulfate. Next, we can solve for the molar solubility of lithium carbonate. We are given KSP of lithium carbonate 2.5 times 10 to the minus 2. This is equal to the square of the concentration of Li plus and the concentration of CO3 2 minus. But since we have 2 here in 2 Li plus, we can substitute 2S for its concentration. So we can express 2S and then squared times S for carbonate ion. So we can have 4S cubed equal to KSP. So 2.5 times 10 to the minus 2, this is equal to 4S cubed. And calculating for S, we can solve for 0.1842 molars. So this is the molar solubility of lithium carbonate. For the third precipitate, we can solve for the molar solubility of silver phosphate. So the KSP of silver phosphate is given by 8.89 times 10 to the minus 17. So 8.89 times 10 to the minus 17. This is equal to the product of the cube of the concentration of silver plus and the concentration of phosphate ion. But since we have 3 here, we need to take 3S as the concentration of Ag plus. So we can express 3S and then cube times S. So this is equal to 27 S to the 4th power. So 8.89 times 10 to the minus 17 is equal to 27 S to the 4th power. So we can calculate for S. So the molar solubility of silver phosphate is around 4.2597 times 10 to the minus 5 molars. So for our last precipitate, we have calcium carbonate. So the KSP of calcium carbonate here is given by 4.95 times 10 to the minus 9. This is equal to the product of the concentrations of calcium 2 plus and carbonate ion. So we can express that as S times S. This is equal to S squared. So solving for S, 4.95 times 10 to the 9th power is equal to S squared, we can solve for the value of S, which is around 7.03 times 10 to the minus 5 molars. So this is the molar solubility of calcium carbonate. So from the choices, you can see that the correct answer is letter A. And that's it for this video. So we have solved 3 problems on precipitation reactions. If you enjoyed this video, please like and subscribe. See you in our next video.